Load the exact same model, same weights, same file, same quantization. They have the same graphics card. They run it with the same tool, and one of them is generating text noticeably faster than the other. Not by a little, by a lot. Neither of them changed the model. Neither of them is overclocking anything. There is no second GPU, no secret quant, no magic build. One of them has a single thing switched on that the other doesn't. And here's what makes this worth 18 minutes of your time. Most people who think they have it switched on actually don't, because the way you turn it on quietly changed, and the old instructions that are still floating around the internet now silently do nothing. So there's a very good chance that if you run local models, you are personally leaving a large amount of speed on the table right now and have no idea, because your command still runs, still loads the model, still works. It just isn't doing the thing you think it's doing. That thing is called multi-token prediction. This video is about what it actually is, why it can make a model dramatically faster, the specific reason it's silently off for so many people, and the part nobody covering this is being honest about, what it costs. Because it does cost something, and there is a real and common situation where turning it on makes your model slower, not faster. I'll show you exactly where that line is, but I'm going to earn the numbers before I give them to you. Because if I lead with, it's roughly this much faster, you'll take the number and leave, and you'll miss the two things that actually determine whether you get that speed up or accidentally make things worse. So here's the deal. By the end, you'll get the real speed up range, the exact command that works today, and the precise hardware line where this flips from help to harm. To use any of it safely, you need the mechanism first. Let's build it. 3 things. First, what multi-token prediction actually does. Not the marketing, the mechanism, in a way you'll be able to explain to someone else in one sentence. Second, the silent off problem. I read the actual source of the most popular local tool this morning, and the real story is more useful than the one going around. And third, the catch. The 2 dials that decide whether this helps you or hurts you, and the hardware situation where the honest answer is leave it off. Standards note, the mechanism and the flags in this video I verified in the source this morning. The actual argument definitions in llama.cpp, the actual model architecture. The eye-popping speed figures floating around are community and vendor numbers I have not reproduced on my own bench. So when we get to them, you'll hear exactly how much weight to put on them and why the honest answer is a range, not a headline. Let's go. Why a model is slow in the first place. The bottleneck you have to see. To understand a speed trick, you have to understand the slowness it's beating. And this is the part most explanations skip. So sit with one uncomfortable fact about how a language model generates text. It is not compute-bound most of the time. It is memory-bound. Here's what that means. When the model writes one token, it has to stream a large fraction of its weights out of memory and through the processor to do the math. Then, to write the next token, it does it again and again. One token, one full trip through the model's memory. The graphics card's raw math capacity is barely breaking a sweat during this. It spends most of its time waiting for weights to arrive over the memory bus. The bottleneck isn't thinking, it's fetching. That's why a local model can feel like it's typing one careful character at a time. Every token is a separate, expensive trip to the warehouse. And the cruel part is that the trip costs almost the same whether you bring back one token's worth of work or several. The expensive part was making the trip at all. Hold that image because it's the whole key. The trip is expensive, the cargo is cheap. Any trick that lets one trip produce more than one token is going to feel like magic. And that is exactly the door multi-token prediction walks through. What multi-token prediction actually is? The mechanism, plainly. Now the idea, and I'll build it so it stays with you. Imagine the model is writing a sentence and the next few words are genuinely easy to guess. The cat sat on the, you already said, mat in your head. A big model burning a full memory trip just to produce the obvious word mat is a waste of a trip. The word was predictable. What if something small and cheap could guess the easy words in advance, and the big expensive model just checked the guesses instead of generating each one from scratch? That's multi-token prediction. There are 2 parts. There's the big model you already have, and there's a small extra piece, a lightweight head bolted onto it, whose only job is to cheaply propose the next several tokens, a draft. The draft is fast because the proposer is small. Then the big model does one thing it's very good at, and which is much cheaper than generating. It looks at the whole proposed draft at once and says, in a single trip, yes, 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 no. Every token it agrees with, you keep for free, because they all rode along on one trip. The first one it disagrees with, you throw away the rest and fall back to generating that one normally. That's the entire trick. A cheap assistant guesses ahead. The expensive expert verifies in bulk. You keep the run of correct guesses. When the guesses are good, one memory trip yields several tokens instead of one. The warehouse run brought back a full cart. And this is why the technique has a formal name you'll see in the literature: speculative decoding. The draft is a speculation. The verification is the reckoning. Multi-token prediction is the flavor where the model ships with its own proposer baked in, instead of you having to bring a second, smaller model to do the guessing. Qwen's newer models include that baked-in head, which is why this conversation is suddenly everywhere. There's one more knob worth naming now because it decides how aggressive the bet is, how many tokens the proposer guesses ahead in a single draft. Guess 2, and you rarely miss, but you rarely win big. Guess 8, and when you're right, you leap forward. But one wrong guess early in the run throws away all 8. There's a sweet spot. It depends on how predictable your text is, and the source shows the tool is actively getting smarter about choosing it automatically. File that away. The depth of the guess is itself a dial, and the best setting is not as deep as possible. Notice what this means, and it's important for later. The speedup is entirely a bet on predictability. When the text is easy, boilerplate, common phrasing, structured code, the guesses land and you fly. When the text is genuinely surprising, the guesses miss, you keep falling back to normal generation, and you've paid for a draft you threw away. Nobody tells you this part. We'll come back to it because it's half of the catch. The Architecture Wrinkle. Why this model is a strange case. One detour, quick and worth it, because this particular model makes the story richer. The Qwen model everyone's running this on isn't a normal transformer. I covered its architecture in full in an earlier video, so here's just the one relevant fact. 3 out of every 4 of its layers don't use traditional attention at all. They use a linear attention scheme, gated delta net, that keeps a small fixed-size running state instead of the ever-growing memory that normal attention carries. The org's own newly published description calls it verbatim, a hybrid architecture where gated delta networks combined with sparse mixture of experts deliver high-throughput inference with minimal latency. Why does that matter for a speed trick video? Because it means this model was already built to be light on memory. The thing we just said is the bottleneck. So multi-token prediction is landing on top of an architecture that was already optimizing the same pressure point from a different angle. 2 different teams, 2 different layers of the stack, both attacking memory bandwidth. When you hear later that the speedups can be large, this is part of why. The model was designed to make trips cheap, and MTP makes each trip carry more. They stack. The silent off problem, I read the source and the real story is better. Now the part that's costing people speed right now, and here's where reading the actual source beats repeating the rumor. The story going around is that a popular local tool silently renamed a flag, so the thing people typed to turn this on quietly stopped working. When I went into the source of llama.cpp this morning, the truth is close to that but more useful. And it changes what you should actually do. Here's what really happened. The old flags people have in their saved commands and their blog posts, the draft flags, the ones that controlled this speculative behavior, were not silently renamed. They were removed with a message. I'm reading the argument definition verbatim. Type the old flag now, and the tool tells you, quote, "The argument has been removed, use," and it names the new one. The whole family got reorganized under a new, clearer prefix. So it's not silent at all if you're watching your terminal. The catch is that a lot of people run these commands inside scripts, wrappers, and app front ends where they never see that message. The command fails soft, the model still loads, generation still happens at the old slow speed, and no error ever reaches your eyes. And there's a second, separate flag that's the actual heart of this. Verbatim from the source, there's a flag whose description reads, "Also download the multi-token prediction head, if available." Read that carefully. The head is a separate download. It is not automatically included just because you grabbed the model. If you never pass that flag, you may never have fetched the very piece that does the speeding up. So there are 2 independent ways to think you've enabled this and be wrong. Your old draft command silently no ops, or you never downloaded the head in the first place. Think about how many layers sit between a person and this flag now. You install a friendly desktop app. The app calls a runtime. The runtime wraps llama.cpp. Your old command lives in a note you copied from a blog post a year ago. Any one of those layers can be passing the removed flag, swallowing the message, and handing you a model that loads perfectly and runs at half the speed it could. The abstraction that made local models easy to run is the same abstraction that hides this from you. This is why "I turned it on and saw no difference" is so common, and why it's not your fault. The correct current spelling of these flags is in the description taken straight from the source this morning, not from memory, but knowing the flag is only step 1. because now we reach the part almost nobody says out loud. The catch, the 2 dials, and the number I promised. Everything so far has been upside. Here's the bill. Multi-token prediction is a bet on predictability, and like any bet, it can lose. There are 2 dials that decide whether you win it, and if you don't understand them, you can absolutely turn this feature on and get nothing, or worse. Dial 1, how random your sampling is. Remember, the speedup comes from the cheap proposer guessing tokens the big model agrees with. The more randomness you allow in your generation, the higher the temperature, the more creative you've told it to be. The more often the big model's real choice diverges from the safe guess the proposer made. High randomness means low agreement. Low agreement means most drafts get rejected, and a rejected draft is pure overhead. You did extra work to propose tokens you then threw away. So the same feature that flies on low randomness, deterministic work, coding, structured output, factual answering, can crawl on high randomness creative generation. The feature isn't broken in that case. You've just pointed it at text it can't predict. Dial 2, and this is the one that flips the sign from plus to minus, memory headroom. The proposer head is small, but it is not free. It takes up VRAM, and it adds a little bookkeeping to every step. On a card with room to spare, that cost is trivial next to the speedup, but on a card that's already nearly full, where the model barely fits and you're one hair from spilling over into system memory, adding the head can be the straw that pushes you over the edge. And spilling out of VRAM into ordinary system memory doesn't cost you a little speed. It costs you most of your speed because now you're streaming weights over a far slower path. So on a memory-starved setup, the speed feature can tip you into a slower regime than you were in without it. That is the situation where the honest answer, the one you will not hear in an enthusiastic tutorial, is turn it off. On a tight card, off can be faster than on. The competitor-grade coverage will tell you to enable it everywhere. The source and the architecture tell you there's a line, and if you're below it, you lose. So where's the line, and what's the payoff? Here's the honest version, and it's a range on purpose. On a card with comfortable headroom, running predictable work like code, the community and vendor numbers point to something in the neighborhood of a large speedup, commonly discussed as roughly doubling generation speed, sometimes reported higher on high-end hardware, sometimes less. I am giving you a range and not a single hero number for a specific reason I'll defend in the limits. The eye-catching single figures being passed around were measured on particular cards, with particular settings, on particular text, and at least one widely shared before number appears to be an already slowed baseline, which makes any multiplied by 3 framing a best case dressed as a typical one. The shape of the truth is meaningful, often large, on the right hardware doing the right work, and 0 or negative on the wrong hardware doing the wrong work. The dials decide which one you get. That's the whole video in one sentence, and now you know why. What to actually do. A short, honest checklist. No hype, just the sequence that follows from the mechanism. If your card has real headroom over the model size and you mostly do coding or other structured work, this is for you. Download the head, the separate flag, in the description. Use the current spelling of the speculative flags. Keep your sampling on the calmer side for the tasks where you want the speed, and enjoy it. This is close to free performance for your use case. If your card is nearly full with the model already, test both ways before you believe anyone, including me. Run a fixed prompt with the head and without it, and watch your actual tokens per second. If enabling it pushed you into memory spillover, you'll see the speed collapse, and the right call is to leave it off and reclaim that memory for the model itself. And if you mostly do open-ended creative generation at high randomness, temper your expectations. The feature is real, but your acceptance rate is working against you, and the win will be smaller than the coding crowd is reporting. That's not a defect, it's the mechanism being honest. Honest limits. 5. 1. I verified the flags and the mechanism, not the benchmarks. The argument definitions, the removal message, the separate download flag, the model's architecture. Those I read at the source this morning. The specific speed multipliers circulating online I did not reproduce on my own hardware, and I'm not going to repeat a single hero number as if I had. 2. At least one popular before and after comparison looks like it starts from an already slow baseline, which inflates the multiple. Treat any single dramatic figure as a best case on someone else's bench until you've measured your own. 3. This is moving fast. The source shows the speculative flags were recently reorganized, and there are open changes actively improving how the draft depth is chosen and how these heads are detected, including support arriving for other model families, not just this one. The source shows this same machinery being wired up for models from entirely different labs, which tells you multi-token prediction is becoming a standard layer of the stack, not a Qwen novelty. The exact spelling that's correct today may shift, the mechanism won't. 4. Your mileage is set by your hardware and your task, not by a tutorial. Everything decisive here, acceptance rate, memory headroom, is specific to your card and what you're generating. The only benchmark that matters is the one you run on your own machine with your own prompt. 5. Nothing here is a recommendation to change settings you don't understand. The point of spending most of this video on the mechanism was so that when you do touch these flags, you know which direction each one moves you. If a change makes your tokens per second drop, the mechanism tells you why. Trust the measurement over the marketing. Step back, because this small speed flag is a window onto something bigger this channel keeps running into. For 2 years, the story of making models faster was about the model. Make it smaller, quantize it harder, distill it down. This is a different lever entirely. The weights didn't change. The quantization didn't change. What changed is the loop around the model. A cheap proposer, a bulk verification, a bet on predictability, sitting outside the weights and squeezing free speed out of the memory bottleneck. It rhymes with everything we've watched this month. The harness matters as much as the model, the loop is where the gains hide, the scaffolding is doing more of the work than the parameter count suggests. A model's speed, like its score, turns out to be a duet. The weights and the machinery wrapped around them. Which is also why the honest version of this topic is a range and a pair of dials rather than a headline. A number without its conditions is exactly the thing this channel keeps taking apart. 3 times faster is true somewhere and false somewhere else. And the difference is your hardware and your task. The conditions the headline drops. You now hold the conditions. That's worth more than the number. So here's my question, and I'll pin it below. Run it both ways on your own machine. Head on, head off, same prompt, same settings, and tell me your 2 tokens per second numbers, your card, and what you were generating. A crowdsourced table of real before and afters sorted by VRAM and by task would be more honest and more useful than any single benchmark any of us could publish alone. And it would show in public exactly where the help to harm line really sits. Post your 2 numbers. Let's find the line together. Every link, the exact source file where these flags are defined, the current correct spelling, the model's architecture write-up, and this channel's deeper teardown of why this model is built the way it is in the description. That's the standard here. The mechanism built before the number. The flags read at the source instead of repeated from a post. The catch stated as plainly as the upside. And the one honest figure delivered as a range with its conditions attached. If you'd rather own your tools than rent them, subscribe. That's what we do every single day. I'll see you in the next one.